Now let's see another reaction of the alkali metals, the reaction with water. We'll start with lithium. The metal floats on the water and reacts with it, giving off hydrogen gas. Now for sodium. The same sort of thing happens, although the reaction is a bit more vigorous. All the alkali metals react with water in the same way. Now for potassium. This time you'll see a flame. The heat given out by the reaction is produced so quickly that the hydrogen gas catches fire. It burns with a lilac flame. The next element is rubidium. This time we put a safety screen between us and the reaction. You can see that things gradually become more terrifying as we go down the group. Let's try cesium, our fifth alkali metal.
An airbag is a rapidly inflating cushion that helps to prevent auto crash injuries. When there is a sudden deceleration of the auto, a switch is thrown which triggers the start of a chemical reaction that produces a gas. The chemical reaction employed is the thermal decomposition of sodium azide, NaN3. Upon heating, sodium azide decomposes rapidly to form sodium metal and nitrogen gas. The reaction is exothermic and rapid once it has begun. In practice, an oxidant is added to react with the sodium to form sodium oxide. When the reaction is triggered by a sudden application of heat, the hot nitrogen gas formed by decomposition of the sodium azide expands into the airbag. Expansion occurs in only about 50 milliseconds. After the initial expansion, the hot nitrogen gas cools and the bag partially deflates, freeing the passenger. Notice that no new substance has been introduced into this closed system during reaction. The large volume difference between reactants and products is due to the fact that one of the products is a
smartphones, wind turbines, audio speakers, computer hard drives and displays, compact fluorescent lights, and advanced defense systems. What do all these vital, everyday items have in common? None of them would be possible without the use of rare earth-based materials. Highly refined, exotic-sounding elements such as lanthanum, cerium, neodymium, samarium, dysprosium, and europium that are used to create many of the products that keep our high-tech, green energy world humming faster, more efficiently, and increasingly smaller. For instance, neodymium, used to make the magnets that have enabled speakers, hard drives, and electric motors to get increasingly smaller over the years, while getting more efficient and powerful. These magnets are the fundamental building blocks in many highly popular electronic devices, and are essential to conventional and electric vehicles, as well as the next generation of wind turbines. Lanthanum. This element is used in alloy to produce the batteries required to store energy for electric vehicles. Europium. Without this luminescent mineral, there would be no color in color TV. To put it plainly, most of the products we use every day, especially those vital to the green movement, and many used for military purposes, are impossible to manufacture without the use of rare earth elements. Where do rare earth elements come from? Traditionally, these materials are mined from open-pit facilities in which ore is extracted and refined to produce sufficient quantities of usable end product. While large, proven, high-grade resources and reserves of rare earth minerals exist in the U.S. and in Australia, currently over 97% of the world's supply of rare earth minerals comes from mining facilities in China, which means China is currently responsible for providing materials needed to fulfill not only the manufacturing needs of the world, but of their own rapidly growing society.
How did life begin on Earth? In the 1950s, a classic set of experiments were conducted by Miller and Urey. The Miller-Urey experiments tried to make life in a bottle. A flask containing water and the basic chemical ingredients of the oceans and the Earth's atmosphere is given extra energy and left for weeks. After watching this closed experiment for weeks, it turns out that amino acids and complex molecules and other organic material is created. The Miller-Urey experiments give some sense that complexity can emerge from simple ingredients given sufficient time and an energy source. However, in the 1950s, we did not know exactly what the early Earth's atmosphere composition was. It turns out that the first Miller-Urey experiments used too much methane and ammonia and not enough carbon dioxide. Using a more appropriate composition for the early Earth's atmosphere yields less organic materials, but later versions of these experiments have nonetheless been able to reproduce and produce almost all the amino acids, sugars, lipids, and the 5 bases needed by RNA and DNA. This is of course not the same as producing a replicating molecule, which has never been seen in one of these experiments. And in fact, other chemical constituents are probably needed in addition to a large amount of time to produce the first replicating molecule. But it is an indication that life must have started by building of larger pieces from smaller pieces.